Hi guys, welcome back to the channel. I'm about to start a new project, which is a memory controller for PSRAM. I'm building a small PMOD, you can actually see it behind me, a PMOD board that you can plug into the FPGA board to add more RAM to the FPGA board that I designed. And I'm trying to make 3 videos about this. The first one is going to be why I choose the part that I choose and what's the reasoning behind all the decisions that I made early. And hopefully it's going to help young designers and maybe old designers, why not, to learn some of the techniques or to stay away from all the mistakes that I'm about to make. And yeah, we'll see how it goes. Let me know in the comments if you find this useful. Hi guys, first what part I chose for this. So I decided to go for PSRAM, serial PSRAM. So why? First of all, why serial? So this is a quad RAM or quad SPI, sometimes it's called. It's actually not SPI. It's a quad interface with 4 data lines and two or three control lines. So the reasoning was that I want to put it over a PMOD connector. So the PMOD connector, so just to make sure that we are on the same page, I'm going to show you what PMOD connector is. So this is how it's going to look like. All right, so I have only 8 data pins available, 3.3 volt and ground. Right, so I had to make something which fits 8 connections. Okay, so because of this, the way how this access to this memory works, it's you present data in chunks of 4 bits. So you present the address in chunks of 4 bits, and then you present the command, what you want to read or you want to write. And of course, it's going to be a penalty for this. So it will add to latency. So I can live with that, and I'll come to reasoning about latency as well. But first, pin. I have only 8 pins available. PSRAM in quad RAM interface seems like a good choice. Now I realize this is going to sacrifice the bandwidth, so that's why I went and I was searching for something which can transfer DDR. So when I say DDR, I mean it can transfer on both edges of the clock. This will double the bandwidth. So the information is going to travel between the FPGA and this memory DDR, double data rate. So it will transfer on both edges. So I came about this part made by ISSI, which is a PSRAM, and I'll come back to the PSRAM, DDR quad RAM, right? 200 megahertz. So what this means? It means that the clock is 200 megahertz, but it's going to transfer actually 4 bits on the rising edge of the clock and 4 bits on the falling edge of the clock. Of course, there are going to be, you need to transfer the address and, tell the memory what you want to read or you want to write and all that. This memory, it's quite fast. And it's a good fit for the FPGA that we have on the board for the Spartan 7, which can reach those speeds, especially with a carefully designed PCB. So this is why I choose this specific part. Now, coming back a little bit to the name of PSRAM, what PSRAM stands for. P comes from pseudo. Pseudo means not exactly that. So it's not SRAM. SRAM is in SRAM the information is actually stored by transistors in flip-flops. So because of that, they can't have very large densities. This is actually inside it's dynamic RAM. It's a dynamic RAM which is kind of seen from the outside world as SRAM, a static RAM. So that's why they put a pseudo in front, pseudo SRAM. Okay, now what's the difference between? I just said that static RAM is memory stored on flip-flops. Now dynamic RAM, the memory, the bits are actually stored in capacitors. And that's why it needs refresh. So if it doesn't have refresh, those capacitors, they leak and they will lose the information. So there will be some refresh cycle. So how the refresh cycle works? If you don't access the memory and you have no refresh cycles, the information inside it will fade out. It will be lost. So they have internally a self-refresh mechanism. So from time to time, they just refresh the memory. So, well, yeah, they make like a fake access to those cells and they kind of refresh. Now, if you have a system, and this comes to the architecture of the system, what your system does. Let's assume that your system reads continuously that memory, scans that memory. That's the use case for example, for a display controller. A display controller reads the memory, the frame buffer, the content of the video memory continuously. From first line, it just goes and it reads to the... In that case, you don't need refresh cycles. Why you don't need? Because you're going to access linearly everything anyway. So that is going to refresh the memory. Now, if that's not your use case and you have a computer which is just fetching, instruction or data and reading and writing in the memory in certain places and everywhere and at certain times, totally random, you need refresh. You need to let the part to refresh. So they kind of hide those refresh cycles behind the scenes. So the part does this behind the scene, but that comes with a penalty. And what's the penalty? You want to access the memory, and the memory internally is in a refresh cycle. In that case, it will add to latency. So basically, the memory will tell the controller, the FPGA in our case, hold on a little bit, I need to finish my refresh cycles. Now, how do you know? This is called a collision. So you can read without a collision, if you're lucky, or you can read with a collision, if you're unlucky. Now, when you read without a collision, you will have a certain latency. Latency means a delay. So you say, I want this, and the part is going to give you data after a certain time or a certain number of cycles, clock cycles. That is called latency. Now, the latency, it's something when you don't have a collision, and it's double when you have a collision. And this is all random. You don't know because this refresh cycle happens behind the scene. You don't know where it is. You have no information. So the part is actually giving you a signal, and it tells you that you are going to have a collision or not, so you know when to expect the data. But what I'm trying to say here, that reading, the latency for reading or writing, it's not the same all the time. It depends if you have a collision or not. So you need to keep this in mind. Oh, the data is not going to be like SRAM. SRAM, bang, and you get the data. Bang, you get the data on the next clock. No. This is not going to happen. Now, dynamic RAM, they have this problem anyway. So this is not because this is a 4-bit access or a quad RAM access. No, it's because of the way how the memory works. Now, in the case that you want to use this for video memory, you can actually disable the internal refresh mechanism. You have a register where you can set different things. We'll go to that. So you can disable the refresh mechanism for a certain range of the memory or for the whole memory. So if you know that you are going to have some video data there, you can actually disable, and that will make the reading and the writing more predictable because you will not have that collision happening. But those are, tricky stuff. Now, I'm going to show you the part on DigiKey. So this is the part, is BGA. I know it's not very friendly for most of the hobbyists, but that's the way it is. The part is fairly inexpensive. It's about $3. Now this is the price for large quantity for a tray of those parts. It's about €3.50 when you buy one piece now. Available to order, so they don't have stock. Anyway, this part is manufactured by ISSI. I actually sent them an email to ask for a memory model as in behavioral model in VHDL, so I can test my controller. They didn't reply. I'm not expecting they're going to reply because usually they kind of ignore small companies. But yeah, look, maybe I'm lucky. I don't know. So this is the part that, and now let's open the datasheet. So this is the name of the part. Now this part comes in two flavors. And the difference is here in those letters at the end. So you see there are A parts and B parts. So the A parts, actually, they are low voltage part. They are 1.8 volt, and the B part, or BLL, are the 3 volt part. Now it comes in other flavors when it comes to speed, because some of them they are slower than others. I choose the fastest one, the 200 megs. Now you need to keep in mind that the faster you go, the more latency is going to have. So there is a table somewhere down where it shows you that the part that you choose with whatever termination it has here, it will have a certain latency at a certain speed. Now, usually the higher the voltage, the faster the part. So anyway, let's get on with it. So I'll show you here. I'll show you just the relevant things. Now, I got caught in something here because I saw this 3 volt. I said, oh, what am I going to do with this 3 volt? Because my FPGA board is 3.3, so I'm going to put a regulator there. I'm going to run. So I realized there is a range here, and I said, okay, look, I can set my IOs to be 2.5 or to be 3.3. So probably 2.5 is going to work. But then I realized that actually the supply voltage is a range, it's 2.7 to 3.6. So this part the 3 volt version of this part, it will work just fine at 3.3 volts. So I added the regulator for nothing. I'm going to bypass that regulator. Now I built boards, so with a regulator, but I'm just going to bypass them on the PCB, on the first set of PCBs. So yeah, look, first mistake, yeah, yay. Now, let's get on with so pin configuration. Actually, what's the best diagram here? This is like a block diagram. So you don't have many pins. You have the data pins, which are 4 pins, and then you have the clock and the chip select. So this looks like the SPI signaling, and 3 data pins. Now, obviously, the chip select and the serial clock, they are unidirectional. They are inputs into the memory, outputs from the FPGA. Then you have a reset signal. The reset is actually optional. If you can choose not to connect the reset. I connected the reset because I have the signal on the PMOD anyway, so I'm not going to use it for anything else. You can actually send a command to reset the part if you really want to reset the part. So you have the data pins bidirectional, DDR, careful, and the DQSM, bidirectional DDR. So what is the DQSM? The DQSM is actually quite important because when you make an access, you prepare an access, the DQSM will tell you if you have a collision or you don't have a collision. So the DQSM will become an output, and it will tell you. Now, the DQSM, after you set up the access, it will become a strobe signal. It will let you know who's what, because you need to know because you have a double data rate DDR. You need to know, okay, what's on the rising edge, what's on the falling edge. And then, now for writing, the DQSM actually has a second functionality. So first, when you make a write access, it will tell you, okay, you have a collision on this write access. But then in the second part, you can use it as a masking signal. That's the M here in the name. You can mask 1 byte in the transfer. If you want, let's say you send 2 bytes, but you want to mask 1. Now, the datasheet is not great. ISSI, yeah, you can say whatever you want, is not great. It's actually a little bit misleading. Now, this is how you prepare an access, regardless if it's read or write. So you have, those are the clock cycles. Right? Now, it's a little bit confusing in the datasheet because the command is made of 2 bytes, right? But those bytes, they are not DDR. Now, they are not DDR. It doesn't really matter because it's basically, it's going to be the same thing on the falling edge, on the rising edge. So you put here the first byte of the command, you put the second byte of the command, so you have 2 bytes for the command, 2 clocks. Actually, they're not bytes. I'm saying something is rubbish because there are 4 bits. So 4 bits of command, 4 bits of command. So this is a byte, right? And then you present the other. So why do you need a command? You need to tell the memory what you want to do. I want to read from memory. I want to write to memory. You can read from a register and can write a register. Why do you need register access? There is a configuration register. So in that configuration register, you can actually set different things. I'm not going to go in detail because there are many bits in that. It's a 16-bit register, many things. It's too much detail for this video. So anyway, you tell what you want. And then you present the address. You have the row address and the column address. This is exactly how DRAM works. So you have the RAS and the CAS signals to qualify this. So like row, why do they have this on DRAMs? Because they want to save pins. So usually DRAMs, they come in larger capacities, and because they are larger capacity, they have a lot of address lines, and you can't afford to have so many pins. let's say you have like the 20 address lines. You're not going to put 20 pins just for address lines. So what you do, you actually split them in row address and column address, and you present them in 2 chunks. It's the same here. So because this is serial, you present 4 bits, 4 bits, 4 bits, 4 bits, 4 bits. Right? So this is a byte, this is another byte, this is another byte, and another byte. So you have 4 bytes. So you can address like a lot of memory. Now, not all the bits are actually used in this transfer. Now, this is DDR, right? So on the rising edge of the clock, you have 4 bits, and the falling edge. And now here it actually shows you exactly how this word is actually structured. So you have the command on the first clock and second clock, which is this part, right? And then you have the row address. Now, depending on the, you'll see here they're not all the bits used in all those, the transfers. So you have on the 3rd clock, on the 4th clock, on the 5th clock, on the 6th clock. So let's say this is the 3rd, the 4th, the 5th, and the 6th, right? Okay, and this is what you present in those clocks, right? So let's say on the 3rd clock, on the rising edge of the clock, you present just 1 bit, row address 12. Then on the falling edge, which is this one, this transfer, you present this one. So this part of the datasheet is clear. Very nice, easy to understand, right? Okay, now, those are the commands. So here they explain the commands, how the command. Now this is, you have a bunch of commands. Memory read with continuous burst. Memory read with wrap burst, memory write continuous burst. So let me explain very, very briefly what's the difference between those. And then we have the configuration register read and the identification register and so on. So let's start with the registers. Identification registers is actually read only. So it's like a signature. You read that and you know, okay, I have this part with this capacity, and so you can, if you have software, you can say, okay, I know what to do with this memory because I know what this memory is. Now, configuration register, this is different, and you have read and write. Configuration register, you can read, okay, what's the default state of the memory, what the latency supported and all that, drive strength for the signals, and I don't know, a bunch of other things. So you can modify them from the defaults. Okay, and then you have this command for if you want to put it in sleep. This is more for mobile devices. I don't really care about this. Now, memory read. 2 types of read. It's continuous read and burst read. What is the difference between the two? A continuous read is you set up the address, you say, I want to read continuously. This is the address where we start. And the moment you set up that and the first data starts to flow out, it will just auto-increment the address. It will get the next one, and the next one, and the next one. You can go to the end of the memory. This is very good for video controllers because you set up the beginning of your, let's say, line, when you want to read a video line, and you keep reading until you get to the end of the line. And you have like a one access. Why is good? Because to set up a command, to set up a cycle, it takes that latency. But it takes the latency until you get the first byte out. After that, they just keep flowing. So you have a penalty when you start the command, but then they come like on a conveyor belt. Okay, what is the burst? The burst is when you want to read a certain number of bytes. So I don't want to read 1,000,000 bytes. I want to read a fixed number of bytes. This is good for a cache controller, for example. So, you know, when you make an access, let's say you read programs, you usually don't just read 1 byte. And then you set up again and you read another byte. And you set up again, you read another byte. You read chunks. So the cache controller actually reads chunks because most of the time you read an instruction, but definitely there is a branch somewhere which just jumps to the next 3-4 bytes ahead. So you read in chunks. Now this is good for video as well because you can set up chunks and you can just read. Or it's good for buffers. If you're under a data buffer and you're on a circular buffer or a DMA. A DMA is actually a very good example because you can have like a circular buffer in the DMA. So it's reading starting from here, goes reading 128 bytes, and then it comes over, it wraps around, and it keeps reading the same buffer. So you don't need to set up another address. But anyway, so you have this wrapped burst. Wrapped means it comes back to the first address or not. Now, again, you have continuous burst and wrap burst. Okay, going further. And of course you have different commands for this. Okay. Now, now we are getting into the thick of it. So, this is how an access looks like, right? So you show the command, like we said before, you show the command, and this is, look, always read this, because this is going to tell you what is this all about. So this is a timing diagram with no refresh collision, so we don't have a collision here. At variable latency, read. So read, we are reading, and it's called 1LC operation. Now this is very confusing, this 1LC, and then you go on the diagram and you see here LC equals 4. But this actually stands for something else. So I will explain, because it took me a while to figure out. So now, let's say you set up the command. You tell the row address and the column address. You see the DQS signal is actually driven by the memory low. This means you have no collision. As opposed to the next one, with collision, and you see when you prepare the access, the memory will tell you signal will stay high, which means you are going to have a collision. So you need to sample this signal at the very beginning, because you need to start counting the latency. Now, how do you count the latency? Or why do you count the latency, first of all? Now, you can choose not to count the latency. And why? Because the controller in the end said, you know what, I don't care what's the latency, just tell me when the data is going to show up. And that's the DQS signal. So when you see this, the first clock here, this actually signals that data is about to show up after this. So internally the controller is actually sampling this signal, and when he sees this strobe, he says, okay, data follows. And so basically the controller just sits here in this state until it's getting this signal, and then start reading the data. Now for the collision, it's the same, just this time is going to change. So you can choose when you make the controller, you know what, I'm not going to start counting cycles here. Now it's actually tricky to count cycles. Why? Not because they are difficult to count. It's because you need to know what you are expecting when that you are going to hit the magic number. And in order to do that, you need to make sure you read the internal register, and you need, okay, this memory is going to give me data after 6 clocks latency, or 4 here in this example. So I need to start counting, and when I get to 4, I know data is going to show up. But you need to know that is 4. So if you don't know, you are on dark completely, then you don't count. You just wait for the strobe. And you don't care if it's coming after 6 or after. Now, to make it even more confusing, they don't start counting this latency from the beginning, from the first cycle. No, they started from the 4th cycle. So, yeah, look, marketing. Because when they publish the data, so, yeah, you have only 10 clocks of latency. No, you actually have 14, not 10, because you have 4 here in front. But anyway, so let's get on with it. So this is the difference between a collision cycle or non-collision cycle. Now, this is the data, and it shows up here. And this is a transfer. So you're actually transferring 2 bytes. So you're actually spending, I don't know, a bunch of cycles here just to get 2 bytes. So this is a setup time, which is going to bite you. But that's the way it is. Or you're going to spend even more here in case of a collision. But now, let's go to this diagram. This shows you, okay, this is a continuous read, which has a different command, by the way. I showed you in the table. So you start reading here from, let's say, Q0, they call it. And it keeps going forever. You can get to the end of the memory. This is good for video controllers, because they set up the word from where they want to read, and they just keep going, they don't stop. It's like a conveyor belt after you set up. Now, this is a wrap burst read, so of 16 bytes. So it just starts from this address, they call it address 0, and it goes, and if you keep reading, you don't stop the transfer, it comes back to the beginning, and it gives you this data again. Okay, now, it has a use case again for video controllers if you want to double a line. So you have a line of video and you want to double the line for whatever reason, like upscaling a video for a retro computer, let's say, right? So you have like, I don't know, 400 or 320 lines on an old computer. You want to make them 640, right? To be compatible with the VGA. This is perfect for that, because you have a line of video here and you keep reading the same line twice, right? And on the video, it will show like upscaling vertically by 2. Okay, so now you have this one, right, which shows you that this burst doesn't have to be from the beginning. You can start from address 4 and it keeps going and then it wraps back to address 4, right? Okay, good. Now, writing is a bit odd, but it kind of works the same thing. So you present the command, you present the address, and then you have this latency. And now, again, you can start counting, cycles if you know where you need to stop. But in the same time, why probably you are kind of forced here to count cycles for the simple reason that if you want to mask data, in this case, you need to know exactly, and you need to know when to present the data. So in this case, you need to know exactly the latency. And again, the DQSM signal, it will tell you if you have a collision or not, right? So this is without a collision, with collision, and this is without a collision. You see the state of this. Now, this is a bit tricky because here you sample, so the DQSM is actually an input into the FPGA, and this is where you need to drive. And this example shows that you are masking this data, so you're presenting 2 bytes, but actually the second byte is not going to be written because it's masked by the DQSM signal. Now, I suspect they put this example actually to show you that you can't write a byte. I think you are kind of forced to present 2 bytes. They don't say this in the datasheet specifically, but I need to ask them if they're bothered to reply to me. Anyway, so this is a bit tricky because you need to count cycles. You need to know exactly when to present the data. Okay. Now this is with collision or without collision. Now writing in registers it's quite it shows you exactly the same principle with the wrapping around. Writing to registers is a bit simpler because it's a very simple access. So you command, address, and data straight away. Why? Because it doesn't care about refresh cycles. It's very, very simple, just a register access. So this is kind of easy. Now, when you read from register, you have the same trouble with, latency. But usually you don't read. You're making a read if you want to know, okay, what's the default state of the memory. But if you want to change something, you don't care what it was. You just write whatever you want and hope that it writes correctly. So this access is actually more important than this one. Okay, so this is about the memory. Now, what you can set. I told you that you can disable the refresh. So if you have a memory controller, you don't want to have the refresh because it's going to stay in your way. So you can actually disable everything, or you can disable. Actually, you can disable everything. No, you can disable different regions. Now, this is deep power down. Okay, if you want to power down a device. Output strength, there is a table, so you can set up the output strength if you have long tracks or large capacitance, and you can't drive properly those signals. This is a feature where you have a pre-cycle, the pre-cycle of 1 clock or 0 clock. So the pre-cycle is basically showing you here that you are going to have this extra, where is it? I think on the read cycles. You will have this pre-cycle which is actually showing you the data is going to follow. You can actually have this or not have this. I think by default you have it, but you can actually get rid of it, and I think you are actually saving, you're saving a cycle in the latency. I'm not so sure, but I think you do. Otherwise, I don't see the reason why you have it there. So, yeah, whatever. But when you build a controller, you need to take all those things into account. Okay, so back to here. Yes, so you have this pre-cycle. Now, latency count. Latency count is actually quite, I'm not going to go in detail because it's kind of tricky. Now, variable latency. So variable latency means it can be this or it can be that, depending if you hit a collision or not. You can actually opt for fixed latency, which means it's going to be larger, but it's going to be always the same. So that will simplify a little bit the controller. Why? Because you don't need to monitor the DQMS line if you have a collision or not. You know, okay, this is going to be that. So I'm counting cycles from that point, and that's the way it is. And now wrapped or or hybrid. I'm not going to go in detail. It's a special case of wrapping. Now, burst length. Burst length is actually when you read in burst, which is a different command, the part will actually spit out this number of bytes. So, for example, for a cache controller, if it's a computer which reads instructions, probably you are going to fall on one of those two. If you are memory, probably, and you want to read in burst, yeah, you can go for the biggest one, or you can go just continuously read everything. It's up to you. Okay, so now this is output driver strength. So basically, it's a series termination resistor which is inserted on the IOs, and latency count. Now the latency count, this is a tricky one, because you will have by default a very, how should I put it, conservative value, quite long. So seven clocks. So 7 clocks is actually going to be 10. I'll explain you why, because there are 3 or 4 in the front that they don't count. They don't count them in those 7 because marketing, not marketing. So you can have 7, or you can have 7 plus 4 or plus 3, or you can have the double of this in case of a collision. Now, why you can choose less? Well, you can choose less if you decide to run the clock a little bit slower. So let's say you don't go 200 megs. If you go 200 megs, probably you have to stay with this or even with this, depending on how good the PCB is, how good your timing is from the FPGA. But up to experimentation. So it's a multifaceted experiment. Voltage, part, controller, PCB. So this is a very, as I said, conservative value. Now, okay, I'm not going to go here in detail. What initial? Okay. Initial latency. Yeah, this shows you, for example, the part that I choose 200 megs at 3 volt. Right. Without collision, I will have 7. With collision, I will have 14. Plus the other, which they didn't count, right? So I'm kind of expecting this. Now, it could be that I have to change it to this if things they turn bad, but we'll see. Now, this is another representation of this. Yeah, that's pretty much about the memory. So I need to build a memory controller for this. Now, application. So when I was looking to this part, I think the main application for this is extension memory for video. So it kind of falls into the scheme of things, because I'm going to have so first of all, let's think of anatomy of a video controller. A video controller continuously reads with the same cadence, let's say from the RAM, the video data. Why? Because the display, you can't afford to stop the display, right? Because the image will tear. So you need to keep reading. So you need to make sure you sustain that. So everything comes down to the pixel clock. So let's say for HD, you have 148 megahertz pixel clock. So you need to have a pixel coming at 148 megs. Now this part is 200 megs, 4 bits, but it's DDR. So you get a penalty. You're not going to get 200 megahertz reading out of this memory. No way. Because you have all that penalty to set up, and you're going to get less. So now it's actually worse. You're going to get less for other reasons, because you need to have writes from time to time. Now reading is very frequent in video memory. Writing is not that frequent. Writing is the computer side, which is writing some things in the video memory. So it's not going to happen with the same cadence. So when you make a controller, it will actually have 2 access ports. A video controller, sorry. A controller to access RAM for a video application. You have 2 ports, a reading and a writing port. The reading port should have much higher priority over the writing. So the writing can wait, because you don't care if you're writing those pixels a few cycles later. You're not going to, but you do care if you're not reading at the right time, because the image is going to break. So priorities is going to be probably 8-to-1. So you need to find times when you scan a continuous line and is about to display that, and you have a gap there and you can read. So the writing port should find its way between reading accesses. Okay, so this is from the system point of view. Now, to the hardware design, right? So I made a schematic here. I'm not going to go, it is too simple actually to talk about. So a schematic here, not much, some decoupling capacitors. You have two, actually three power pins. You have those power pins which they power the IOs. They have this Q in the name, and they have this for the internal. So I put here 2.5 volt because I have a regulator in between which I'm going to bypass, but it's actually 3.3. Now it's a connector here and some pull-ups. So not much. Some pull-ups on the signal so they don't float in some stupid states. And of course this regulator which is going to disappear. Okay, PCB design, not much to show there. I'm going to show you the 3D, which I kind of did. Ah, here it is, on a different screen. Okay, this is the 3D. So not much. It's this BGA part, some resistors, and not much, right? Some of the tracks are actually delay tuned, so basically they have the same delays and length. But at this kind of length, it's not that critical. This is the 8 megabyte or 64 megabit memory. Yeah. So we'll see how it goes. So I know it was a long and maybe tiring video. Those are the things that the decisions that I made already. So I made the board. I already have some PCBs. I'm not going. My machines are busy here, so I can't build this PCB. Probably it's going to take another week. But I'm well into writing the controller in VHDL. And I think it's going to be tricky to test, so I'm going to have a video about the code and about the testing on the FPGA and all the constraints that I have with testing, because it's not easy to test, especially if I don't have a model from ISSI. It's kind of difficult to test directly in simulation. I started already the code. I implemented the state machine, and I have the register access, at least the writing access. So I'm expecting that to work, but it's tricky to test because I don't have an oscilloscope which has enough inputs, and I have a logic analyzer which I can use, but it's limited in speed, so I need to slow down everything to a few megahertz so I can sample with the. But I have an interesting technique which I'm about to show you probably in the next video, which you can use in the future, using the board actually to test the IOs. Because the tricky part is that the moment you use the IOs, like DDR IOs, you can use chipscope, which is some sort of internal logic analyzer, or integrated logic analyzer, ILA is called in the tools. The moment you use those IOs, you can't sample them from the inside. So a good technique is actually to feed them out and bring them back into the board on a different connector and sample there, so you see exactly what the memory sees. But anyway, we'll get to that in the next video. I hope you enjoyed. I hope you are still around, and I shall see you in the next one.